Hi! Today I will tell you a story about one time where deep convolutional neural networks lost one of the most primitive techniques in a whole image processing. And all of it happened and was recorded with a fullness of scientific rigor. This episode contains parts of the research conducted and described in two of my publications. The links to them are in the comments. If by chance you're currently writing an article and you need to cite somebody, cite us. Even if you consider my work to be dumb and trivial. If you think so, please roast me and quote me in the paper. I'm really chasing that age index of 6 and there's more than one way to get to it. Like and subscribe will be also appreciated. Thank you very much and lecimy z tematem. There's a dataset, all IDB2, that contains microscopic photos of leukocytes from both healthy patients and sick ones that suffer from the acute lymphoblastic leukemia. Now, acute lymphoblastic leukemia is a horrible disease that kills people, kills adults in around 5 years from the diagnosis. So I'm pretty sure we can all agree that having the automated means of detection, classification and diagnosis of this disease would be much appreciated. Am I right? So we have a binary classification task. We must distinguish between healthy and sick patients. Fair enough. So we usually do it with convolutional neural networks. We've used the MobileNet v2 in the PyTorch implementation. This network was pre-trained on the ImageNet dataset. We've applied it to our problem and we scored 92.8% accuracy on the balanced dataset. Pretty decent, nothing fancy. It's a good start of our research. Of course, later on, we've added the image augmentations to increase the amount of images in the dataset by randomly modifying the images, and the results went from 92.8% to 94.8%. Again, nothing fancy. Just a typical deep learning grind, typical deep learning work. Of course, our model, having above 1 million trainable weights, was... One could say that it was expensive, but taking in consideration the models from other research teams that contained above 50 million trainable weights, they've used the architectures like ResNet 50 to the binary classification, then still our model was pretty lightweight, so to say. Of course, we needed a GPU to train that network, but our university gave us the GPUs and paid electricity bills for training it, so not our problems. However, I decided to do something funny. Instead of interpreting the images, what would happen if I analyze an image's histogram? Instead of applying deep convolutional neural networks to process tens of thousands of pixels that mostly contains redundant data, I would use some machine learning algorithm to interpret a histogram made of merely 31 bits. That seems too simple. Almost blasphemous to consider, but such a task can be accomplished with such trivial ways. But still, I was in a good mood. And I figured out that it is still not funny enough. How about giving to the machine learning algorithm histogram of only one channel? So there would be a model for interpreting only a red channel, only a model for interpreting only green channel, and the model for interpreting only blue channel. I also added the HSV encoding to spice things up, so there is also the models for interpreting a hue channel, value channel, and saturation channel. That can go right. Am I right? But actually, the results are even better. It turns out that interpretation of a green channel by XGBoost model, interpreting the histogram, merely histogram, 31 beans conducted from the image and interpreted by XGBoost algorithm, did the trick. It scored 96% accuracy instead of the best result from neural networks, which is 94.8%. Of course, the values I'm telling right now are the averages of multiple iterations of the experiments. So some models scored better, some models scored worse, but the metric that was used in this particular example was the average among iterations of the same experiment with the same parameters. So, to iterate it, the very, very easy, trivial solution of merely doing histogram analysis of XGBoost, something that can be done on the ESP microcontroller, which costs $2, one with the absolute behemoth that is deep learning run on the Tesla A100 GPU. Now, why did it happen? Why did neural networks lose? The answer most likely lies in the amount of data. Our IDB2 dataset contains of merely 260 images, which is 130 per class. When you have such little data and you have to use it to train above 1 million of trainable weights, it is not much. So the less data you have, the more you must rely on the data preprocessing, and you should use lighter models. Of course, the research conducted in these two articles spans a broader area than just the classification I mentioned in the episode. However, I still found it fantastic and I wanted to share this observation with you. That's all for today. Thank you for watching and see you in the next episode.